Log on, tune in, find out. Another good idea from Cambridge.
Now we have Richard Chandler, who's going to tell us all about how to do this with the multi-model. So everyone take notes.
Okay, thank you to the organisers for allowing me to speak. So, for the benefit of the few people who were at my talk 4 weeks ago or so when I was visiting here, there's a lot of overlap here, but I have actually achieved quite a lot since then. So if you wake up in 15 minutes or so, that is probably appropriate. This morning we heard a lot about how to deal with uncertainty, if you like, under the bonnet of climate models. So John T and Michael and Michelle were talking about sort of, trying to find the parameter settings, to learn about what the values of the parameters should be. My concern is slightly different. I'm coming at this from the perspective of a hydrologist or a building engineer or an ecologist or somebody like that who wants to learn about climate change impacts and goes to the CMIP3 archive where there's a whole bunch of data from different climate simulators, and they go, what am I supposed to do with this? So I think this is all fairly standard. We've reviewed a lot of this. So I'm going to be talking about multi-model ensembles, how to combine information from multiple climate simulators and how to provide relevant probabilistic assessments of uncertainty. I don't need to talk much about this because David has done a good job of preparing the background here, so we could use multi-model means, and we've talked about some of their disadvantages. We could try and weight the individual climate simulators, but there are various problems with that I indicated yesterday in my question to Matt. Another thing that we haven't touched on is that typically in any climate impacts application, you're interested in several different quantities, several different outputs from your climate simulators. And there's no guarantee that the ranking of the simulators will be the same for every one of those quantities. We know that there is no one GCM is uniformly better than any others for all properties that you might think of. And to try and attach weights to simulators fails to recognize that. Okay, I'm not going to talk about that one, but what I'd like to do, and this is a slide I put up at the Exeter workshop, is to just illustrate that particular point. So I've got some artificial series here. So the black one is, if you like, monthly mean temperature time series as observed. Okay, the blue one is a climate simulator that's got, the mean is not too bad, but the seasonal cycle is obviously massively underestimated there. And there's a red simulator here that has a reasonable seasonal cycle amplitude, but a rubbish mean. Now, supposing that I'm doing this because I'm interested in some agricultural application, and I'm interested in the growing season for a particular crop, which I'm arbitrarily defining as meaning that the monthly temperature is in excess of 12 degrees centigrade. If I calculate the length of the growing season for each year of this simulation, according to the observations, okay, it goes like that. According to the blue simulator, it goes like this. So the blue simulator underestimates the length of the growing season because it doesn't have a large enough seasonal cycle. Okay, so it never gets hot enough in the summer, basically. The red one underestimates the length of the growing season because it's just too cool generally. So if you were to, so basically the red one's got a decent seasonal cycle but a rubbish mean. The blue one's got an okay mean but a rubbish seasonal cycle. And if you weight them, then as far as your impact model is concerned, the length of the growing season is going to be somewhere, weighting gives you an answer in between the two. So it's going to be somewhere in that grey region. And I would argue that what we ought to be doing, rather than weighting simulators, is we should recognise that one of these is good at one thing and one of them is good at the other, and we should reward that. And in this paper with a PhD student of mine, Nadia Leaf, both of whose external examiners are in the room actually, we are. Sorry, she's got a PhD. It's, we argued that it would be good to have a framework that is able to reward the strengths of individual simulators, and actually we said penalise weaknesses, but I'm older and more relaxed now, and I think we should discount the weaknesses. Okay, the full reference is in the abstract. So that's an example I'll come back to later. There's another issue in terms about probabilistic uncertainty assessment for multi-model ensembles, which arises from something, another thing that David touched upon in his talk, which is that let's have a look. The available climate simulators, in particular the GCMs, don't sample the full space of the simulators that we might have developed if we had lots and lots of resources. And this is often described as an ensemble of opportunity, or as you might describe it, an ensemble of missed opportunity. So there have been various attempts, statistical attempts, to analyse multi-model ensembles within a probabilistic framework and to issue probabilistic, a summary of uncertainty in a probabilistic way. And the seminal paper here is from Tibaldi et al. In the Journal of Climate. But it's not quite clear that those probabilities are really relevant to any decisions because of the fact that this we're not really quite sure what this ensemble represents in any statistical sense. Hence the calls from people like Jonty and Michael, perfectly rightly, to develop frameworks that allow transparent and defensible judgments in order that if I give you a probability statement, you know where I'm coming from. Now, so what I'm going to do is to start by describing rather briefly the conceptual framework that Nadia Leith and myself developed, and it starts from the observation that when you have projections, future climate projections from a climate simulator, they are not intended to reproduce, they are not predictions. Okay? They are intended to get, say, the mean climate right or the variation right. So they won't give you the exact temperature that's going to be that it's going to be in Cambridge on the 1st of January 2070, but the PDF, in an ideal world, would be about right, averaged over some space and time scale. So as statisticians, our interpretation of that is that the outputs from the different climate simulators should have a similar structure. Okay? Cambridge is warmer than Aberdeen. All right? And the point about that is that it can be described using the same form of statistical model, but with different statistical parameters. And I'm going to show a graphic to explain this in a moment. The statistical model is an emulator. It's not an emulator in quite the same way that Peter is going to talk about it, but it is an emulator in the sense that it is a statistical description of the structure that we observe in the simulator outputs. And what I'm going to do is to establish a distribution for the statistical parameters in my emulator that characterizes what I like to think of as a population of climate simulators, but which other people in the room might prefer to describe as an infinite exchangeable set. Operationally, I think they play the same role. So let's see how that works graphically. So with apologies to people who have heard, I always describe this slide in the same way, so if you've heard it before, it's, I apologise. So climate simulators are black boxes, unless they haven't been invented yet, in which case they're pale blue boxes. Okay, so each simulator produces some output, which in these cases, time series. The outputs have some common features: trends, oscillations, some irregular components. The trends can be characterized by their slopes. That slope is a parameter in a statistical model, as is the amplitude of the oscillation. Okay, so I can write down a statistical model which has the data in it from this simulator, described by some parameter, the slope, the oscillation, etc. And what I would like to do then is to take these thetas, these parameters in my statistical model, and characterize the variation in those thetas by a probability distribution. And I claim that probability distribution represents climate simulator uncertainty. Now, for a formal framework of this, I mean, this is actually a hierarchical model. Statisticians call this a hierarchical model because there is a hierarchy of levels of randomness, if you like. First of all, you've got the data, the y's, drawn from distributions with parameters theta. But the thetas themselves, from the different climate simulators, are subsequently also drawn from a distribution. So there's two levels of randomness there. For hierarchical models, I mean, I'm not going to talk too much about this, but calibration is easiest in a Bayesian framework using Markov chain Monte Carlo methods, and that's how we normally do that. As Matt said in his talk yesterday, this can be difficult, and I think that's probably a barrier to widespread take-up of these things outside a rather specialist community, and later in my talk I'm going to give a poor man's version that enables you to avoid doing this completely. What we can do, if we want to generate future climate scenarios for impacts studies, accounting for uncertainty, what we have to do is we have to do our Bayesian stuff to get a posterior distribution of theta. We're going to sample a theta from that distribution, and then we're going to use our statistical emulator to generate the corresponding data. Okay? And essentially what we're doing then is we're generating loads and loads and loads of pseudo climate simulators and using those to characterize the uncertainty in the multi-model ensemble. So if we go back to the example I showed with the growing season, okay, I had a temperature time series there, yt, okay, time t, and I might characterize those time series as having some underlying mean level plus there's the annual cycle. Actually, it was a monthly series, so that should be 2 pi t over 12, but never mind. And there's a trend term in case there's, I mean, this is a very, very simple toy example that's intended just to fix concepts. Okay? Those time series might be, I mean, this isn't actually the model I use to generate them, but it's a reasonable descriptor of the structure in there. So there are 1, 2, 3, 4, 5 statistical parameters in that model. That is my parameter vector theta. Okay, which summarizes the structure of the data. So that's my conceptual framework. There are two key innovations, I think, here. The first is that I'm going to throw away the data and replace the data from each source with the maximum likelihood estimator of the statistical parameter vector. There are 3 reasons for doing that. One, the maximum likelihood estimator is asymptotically sufficient. Basically, I can do that without losing any information. Okay? Because this is typically of much lower dimension than the data, it speeds up the computation. The MLE asymptotically has a normal distribution in most in most standard problems, although somebody's bound to come along and apply this to a tipping point problem, which it doesn't. And the covariance matrix of that normal distribution can be estimated straightforwardly. And within my hierarchical the second innovation is I'm going to use my hierarchical modeling representation to introduce an explicit representation of this ensemble of opportunity. I'm going to show how to do that now. So that stuff had all been done before the program. The rest of the talk is what I've been doing while I've been on the train between here and London. So within this conception, climate is there. Okay? Climate is described by a set of statistical parameters, theta 0. y0 is the climate observations, which I've reduced to the estimate of theta hat 0. I've got a bunch of m climate simulators over here, which have each got their own theta, which is, these arrows, this is like one of Michael's diagrams before, except that I regard these arrows as causal. Okay? That means that if actual climate changes, I would expect climate observations to change. It's not very controversial. I would also expect the properties of climate simulators to change because the modelling groups would go and tweak all their buttons and things and recalibrate them. Okay? But we know that climate models, climate simulators, are imperfect, so the thetas you get for your climate models don't depend just on the actual climate, they depend on, they've got all this nasty stuff, the biases, okay, in all of their properties. And the problem is that these biases, because of the unsystematic way in which climate simulators are sampled, there's something nasty down there. Right? And I said, here lieth ye root of all evil, because that is really the problem about multi-model ensembles. So, as Michael also said, once you've drawn a diagram like this, you're able to decompose the joint probability distribution, and you're able to say things like, well, what I want to know about actual climate, theta 0. The data I have are theta hat 0 from the observations, and the things from the climate simulators. And I can use my directed acyclic graph there to discover that if I think that that is the structure of the data, the posterior distribution of Bayesian framework factorizes in a slightly different way to the one you're used to being taught. It's the prior times the product of two likelihoods. One is the likelihood that you get from the climate simulators, and the other is the likelihood that you get from the observations. And that factorizes really nicely. So that is completely general. To get any further, I've got to make some judgments. And what I'm going to do now is I'm going to analyse a rather simple case in which my judgments about everything are that they're all Gaussian. So the MLEs are multivariate normal, centred on everything. So for those who were at my talk previously, this is different now because I'm allowing potentially different internal variabilities for each climate simulator. The biases are multivariate normal, centred on this thing that is a really nasty thing. So the idea is that real climate is over here, and because of the way that climate simulators have evolved and everybody shares information, they're somewhere over here. Okay? And the difference between them is that skull and crossbones. Okay? So I'm going to say that these biases, if you like, are centred in the wrong place with some covariance matrix, and I'm going to assume that that has a normal distribution as well. Now, I can make some comments on that. So, okay, this is a simplified case where I'm assuming that everything is Gaussian, but actually those Gaussian assumptions are not that restrictive. Okay, I mean, there are situations in which you wouldn't want to make them, but I think they're sufficiently unrestrictive in practice that this situation can give us a lot of insight into what's actually going on in a multi-model ensemble. I'm aware of the time, so I'm not going to go through them in detail, but trust me. You're going to need to remember the notation here, because it's quite important in terms of interpreting some of the results that we get later on. So J represents internal variability. Okay, I'm trying to translate these things into sort of climate speak. J represents internal variability. C's represent the lack of consensus of an individual simulator with the overall simulator means. Okay? C for consensus or covariance. Lambda is the covariance matrix of this nasty thing, and that represents the propensity of simulators collectively to deviate from the actual climate. And I'm afraid I'm going to introduce one last piece of notation, which enables my equations to fit onto one slide. I'm going to write D is J plus C. So it's the sum of internal variability and lack of consensus. Having done that, I can look at the posterior, and all of these things are Gaussian. And, you know, I'm really proud of this, but I'm just going to have to skip through it. I've inverted a massive matrix, right, analytically, and I'm really pleased with it. But anyway, what you find if you do this is that the posterior distribution of actual climate, given all of the information, is a multivariate normal with mean vector Tor and covariance matrix S, and they've got these quite intuitive expressions. They're nasty, but they're easy to program in R or MATLAB or anything like that. The bits of them come from the prior, the observations, and the climate simulations. And what we can do now is we can look at those expressions and we can learn an awful lot about them, about how to interpret the results of a multi-model ensemble. If you look at it, okay, here's the posterior mean. Mu0 is my prior mean. Theta hat 0 is the information I've got from the climate from the actual climate. Theta hat I is what I've got from the simulator. So this expression is a matrix-weighted average of the information from the different sources. Let's look at it. The posterior precision, which is the inverse of the covariance, is given by that expression there. So what I'd like to do is to make, we want to make the posterior variance as small as possible, the precision as high as possible. If J0 goes to 0, this thing's going to go to infinity, and the precision goes to infinity. Increasing the number of relevant observations tells me everything I need to know. That's not a surprise, right? Increasing the number of climate simulators. Well, as n goes to infinity here, maybe I can make this bit go to 0, but that lambda will always be there. And that limits the precision of any multi-model ensemble. Right? You cannot get arbitrarily precise just by funding more and more climate models. You can think about increasing the length of the simulator runs. Okay, the same thing happens, and we can learn an awful lot about all different things that we might want to do, and look at the effect on that expression, and we start to understand maybe things that we should be doing with multi-model ensembles. What about the posterior? Sorry. 5 minutes. Okay, thanks. What about the posterior mean? Okay, so this is, if you like, your point estimate of climate. It has that expression there. Because it is a matrix value, the weights are matrix valued, each component of the climate gets different weightings for the different information sources. Right? So you're not weighting simulators, you're weighting simulators differently for each different component. So you are rewarding the strengths and discounting the weaknesses. One thing that I think is really nice about this is that the weights emerge, these weights have emerged from thinking about the structure of the data rather than about thinking about, well, I should reward something that gets close to the simulations that are close to the actual observations or anything like that. I haven't made any heuristic decisions. I mean, you could argue about Gaussian things and all the rest of it, but I think these things are actually not too difficult to make judgments about, or at least to think about. Right? And the weightings emerge from that. The weights are I was expecting, when I started this, to find that the posterior mean would have something in it with a discrepancy between simulated and observed climate. It doesn't. And I was really surprised about that. But all that is in here is the covariance matrices, which are about expected discrepancies. they're about expected internal variability, expected deviations of one simulator from the mean of all the simulators, and expected deviations of the simulators collectively from the real climate. And the weightings come from that. We can also think about the role of climate observations in all of this when we're making future projections. So in practice, what our theta is likely to be is to consist of some parameters for a historical period and the corresponding parameters for the future period. And we can use this to do all of that as well. And we can, for example, the historical observations make no contribution, are uninformative about the future. Okay, which means that the precision matrix from the observed component has a 0 in for the future part there. I will point out though that historical observations are relevant for calibrating the model, for estimating the J's and the C's and things like that. So it's not like they're completely useless. But I think the point about this slide is that although the historical observations are not relevant for the future, historical simulations, 20th century simulations from the climate simulators are. And we can think about the structure of these matrices to figure that out. Now, I said, I'm rushing through this, but I'd like to finish with a poor man's version of the whole thing. Because as I said before, to do this properly requires MCMC, and it takes a long time, and people might not feel comfortable with that. I'm going to cut some corners, because I'm going to say, having got my expressions for the posterior, I can estimate all those quantities and I can plug them in. What I get will ignore the statistical parameter uncertainty, but I would argue that it's much, much better than what is commonly done at the moment. So the J's can be estimated directly. Any software package will give you those. I can estimate the C's as the sample covariance matrix of what I get out of my simulators. And I've only got one observation of this, and I'm going to use my one observation to construct an estimate of of lambda. And it requires a judgment, and the judgment I love being able to do a skull and crossbones in latex, so I've taken every opportunity to do it. I've even put hats on it. Look, it's backslash skull, and you need a skull package to do it. So this is the covariance matrix of this thing, the estimated covariance matrix for the historical period. And by setting the matrix like this, what I'm saying is that simulator biases persist into the future. That's an example judgment that I might choose to make. You might say that they persist into the future and they might get a bit bigger, in which case I might put, say, 1.2 lots of this down there. But, I can do that. Now, I'm going to show how that, if I apply this to the crop growth example, so I'm going to fit that emulator separately for each data source and time period. I'm going to assert complete prior ignorance of the parameters, which is not very sensible, but it was 2 o'clock on Monday morning that I was doing this. I couldn't be bothered thinking about it. So I fitted that model. Here's the historical period. Okay, those are the parameters that I get from the observations, parameter estimates. These are the parameter estimates that I get from our climate simulator 1. Notice that this value here, which is the intercept representing the mean, okay, is too low. This is the simulator that is biased down because it has too low a mean. It's got this beta 1 is essentially the amplitude of the seasonal cycle. There's the observations. Simulator 2 is biased down there. Right? Now, I'd like you to just look at those and think about what do you expect that massive matrix formula is going to give you for the expected for the posterior mean in the past and in the future, given that that's what the simulators give in the future. Give you 10 seconds to think about that. Now, if you look at it, I mean, it's unsurprising that it basically reproduces the observations here, because we've got those, and they are the closest thing to the actual climate. But in the future, look, we've got the 7.57, 11.52, and it's come out at 11.75 and 4.98 there, even though one of the simulators is massively low there and another is massively low there. Now, I've stared at this, and I am absolutely baffled as to where that comes from. Because, I mean, in terms of the matrix formula, it turns out what it's actually doing is it takes the average of these two in the past, and it finds a bias as the difference between the historical observation and the average of those two, and then it basically adds that back on to the average there. That's what numerically is happening. But I'm completely gobsmacked as to, I mean, I can't see where that comes from in how the formula is doing it. Well, I feel as though I've sort of opened up a flower, you know, and it's one of those mathematical things that I don't understand. But I mean, I don't feel as though I take any credit for this. All I've done is written down a matrix, and it's just beautiful. So I apologise. I'm quite excited by this. But I think, well, I'll put up my summary slide there because I have gone over it a little bit. But thank you for your attention, and if you gave it.
We'll have one or two brief questions. We want to question the transparency? Yeah.
I don't understand why you're saying that you don't have a comparison between the models and the observations. In fact, in the last result that you have, you say that in the future you take into account the observations and the models to get the projection.
But nowhere is that done directly.
No, but I mean directly, okay, but you keep it, you somehow you rank the models on the basis of the fact that
I don't do that.
well, that algorithm that you have.
I mean, what I think the point I'm saying is that I make judgments about specific expected discrepancies. None of them are the discrepancy between the model, the simulators, and the observations. From those judgments emerge automatically that result. So I don't have to worry about how to compare simulators and observations. We can talk about it later, maybe, if there's.
Okay, so we'll have one more question, but in the time that David is actually asking his question, Peter, can you come up and...
Yeah, recently people have been showing plots of variance of ensemble mean versus number of models in the ensemble, and it doesn't go down as 1/n, it sort of saturates.
Yeah.
I was wondering if your model, your statistical model, will capture that effect.
I think it
It'd be really
would.
nice
Because,
to see that.
yeah, I think it probably would because of that last term which had that lambda in it, and as you increase m,
That's what I was
it's going
thinking.
to reach.
They came out with a parametric form for that thing, but just empirically. But it'd be
Yeah,
good
well,
to see
I think
your
that
thing and see how well it fit that.
I think that would do that.
It'd be really nice to see that.
Okay, excellent.